Hello and good day. My name is Ben Dannon, and thank you so much for coming to our presentation on partial inductance, the secret to correlating simulation and measurement. I'm presenting this paper that was done with Steve Sandler, Heidi Barnes, and myself. Here is a brief overview of what we will be discussing today. We'll start with talking about the mounting inductance definition, and then going into how we simulate that mounting inductance, and finish and summarize with how to measure it. Okay, so let's start by looking at a representation of a capacitor mounted to a PCB. Here on the left, we're showing you a 2D representation of a capacitor mounted to a PCB. And what you see on the right is the SPICE model that represents all the parasitics that correspond to that 2D model on the left. And as shown by the parasitics on the right, we can see that we have to include plain inductance, ground via inductance, the inductance from the solder, the RLC component for the internals of the capacitor, as well as the physical path inductance. All that makes up this represented mounted component model. If we were to take that PCB and import it into an EM simulator like PathWave ADS, and then short the pads together, this is the result of what we would get. On the graph, you see a shorted mount, and what we've done is we've extended these pads to a short. And the copper in the simulation is a sheet or a near zero thickness. And what we're showing is that we're seeing 495 picohenries for that inductance of this shorted mount. If we think about this from an equation perspective, we can approximate what the inductance of these pads of the shorted mount should be per Frederick Groover, and that's shown in the blue box. We know this because inductance is a function of the length of copper, the width of copper, and the thickness. In addition, the length is also a function of the precise placement of the ports within the pad. So in reality, this is really the first correlation of the inductance from a PCB mount that should be made. It should be made at this level. Okay, so if we were to perform a measurement and try to compare the shorted PCB mount to a capacitor on that PCB mount, that's what we're showing here in front of you. And that's what we did. What we did is we did the measurement by removing the PCB characteristics using a de-embedding. And you could also do this with calibration. A ground isolator was used with a 2-port probe, and that ground isolator is needed to minimize the ground loop at low frequency. So what you see is the red trace is showing you a classic capacitor plot with the downward 1 over omega C decreasing Z at low frequency and omega L increasing Z at high frequency. The blue trace is the trace of the shorted PCB mount. And what you can see is the shorted PCB mount measures 430 picohenries, not so far off from what we simulated before at 495 picohenries. Now keep in mind that the measurement uses a short that is not near zero thickness. Unlike with an EM simulator, this may not be exactly the same as the PCB trace width. Ideally, the short should identically match the physical capacitor size. The capacitor measures 130 picohenries higher than the PCB short. So this is really the excess inductance of the capacitor element with the physical length element removed. That 130 picohenries is the ESL that we need to enter into our simulator, our simulator for correlation. So we can remove this inductance of the mount prior to the measurement by performing a fixture removal calibration. And in this case, we set the calibration inductance of the shorted PCB to 0. Here, the red trace shown is the same capacitor trace from the previous slide, where the blue trace is the capacitor on the same mount after de-embedding the physical path inductance. Now, remeasuring the capacitor results in 144 picohenries versus the red trace, the uncalibrated measurement of 560 picohenries. So keep in mind that it's really hard to achieve a perfect correlation of sub-nanohenry values, and it's quite difficult. So don't expect perfection. The thickness of the solder joint, the alignment of these capacitors on the pads, and the point of contact with the capacitor all have an impact. In addition to the differences in the physical size of the short used for calibration, the simulator has an infinite dynamic range and a near zero noise floor. The measurement does not. Still, it's good, or it's important to try to replicate that the measurement and the simulation are as closely as possible for correlation purposes. Okay, so let's look at some actual vendor capacitor data. Looking at the ESL from two Murata capacitors, specifically 1 microfarad 25 volt rated caps, looking at Murata's proprietary sim surfing software, you can see at 50 megahertz where we will also be measuring, you can see there's 400 picohenries and then 340 picohenries. And what's interesting is that we see that the thicker capacitor measures at the 400 picohenries, whereas the lower inductance is likely the result of calibration or of the contact point with the capacitor. This is also likely a probe contact point measurement on the capacitor pads, which will be shorter than the full 2 millimeter length of the capacitor body. In other words, the length inductance is different. As a note to reference, the PCB pad center to centers are 1.9 millimeters. That'll be important in the next slide. Looking at another capacitor from AVX and measuring the center to center difference between the terminations, we get 1.6 millimeters approximately. And we can say that that's 15% shorter than the Murata pad center to center difference. The measured width of this 1.27 millimeter capacitor from AVX is, the measured width is 1.27 millimeters for this AVX capacitor, which is approximately 6% wider than the AVX, or 6% wider than the Murata part. Now, using the Grover equation that we showed before, also showed there at the bottom right, we can recalculate what the inductance should be based on these measured dimensions. And what we get is 345 picohenry. Now, if you recall, based on the sim surfing software, this 345 picohenry is somewhere in between the two Murata curves. Using the AVX proprietary simulation tool, their vendor data for this capacitor is showing 709 picohenries at 50.39 megahertz. That's interesting because clearly AVX had to not remove the fixture from their measurements. If this 709 picohenry was entered into the EM simulator, the simulator would add an additional 495 picohenry for the PCB fixture. Remember, we showed this in simulation. And so that would result in a total ESL of 1.2 nanohenries, more than double the correct answer. What this tells us is that neither Murata or AVX include any description of how they measured their capacitor for inclusion in your simulator. This is the reason why we recommend you measure these capacitors for yourself. Well, I mean, maybe the question on your mind is, why do you care if these vendors don't provide measured data for these components? Well, I can think of multiple past printed circuit board designs that I did where we designed PDNs, or power distribution networks, and consumed significant valuable real estate on the PCB to fit more capacitors than we needed to in order to meet our impedance targets. We knew the PDN was over-designed since we made measurements to correlate to our simulation. If we had had better component models, we could have saved costs by reducing the capacitors and saved valuable space on our PCB. So let's look at some actual measured data for these 1 microfarad capacitors, specifically 2 from Murata and the 1 from AVX. What you see is the graph on the left is a representation of the impedance measurement of the 3 capacitors. The graph on the right is the measured the ESL, which is calculated from the measured impedance measurement, or derived from the impedance measurement. So the first question you should ask is, what are we expecting to see? How do we know that the AVX cap should be the same as the Murata cap? And that's simple, right? Look at that Grover equation that we showed previously. That inductance is mostly a function of the chip size. So we know what ballpark we need to be in. And we know that by considering that inductance is calculated on this Grover equation, which is the majority of the inductance of these capacitors. So comparing the measured data to the vendor data for these two 1 microfarad capacitors from Murata and the 1 microfarad AVX capacitor, we see a difference of 252 picohenries, 166 picohenries for the two Murata caps, and 569 picohenries for the AVX capacitor. That's a significant difference. If an important observation that I take from that is that all the capacitors from this Murata and AVX are also 1 microfarad and the same package size. And so if we look at the impedance plot there shown on the left, we see that the impedance for all these caps have a slightly different resonance point. This tells me that all 1 microfarad caps, even though they're in the same or similar package size, are not created equal. And we can attest that this is due to the variation of the internal element inductance of these caps. The last thing that I'll leave with on this slide is that after measuring all kinds of caps, special low ESR caps, there really is little difference. An 0805 package size has so much inductance, most of which is due to the size of the component. If we could make the excess inductance zero, as shown earlier when comparing the mounted capacitor to the shorted PCB mount, it would still only save 130 picohenries. And of course, we can't make it zero. So how do you account for the mount? If you will be using the S parameter measurement for simulation, perform the fixture removal calibration using a short that is as close as possible to the capacitor dimensions. Then measure the capacitor and export the result for simulation. That will result in the 144 picohenry inductance difference that we showed previously. If you are creating a broadband splice model of the capacitor, you can use the method that's shown in How to Design for Power Integrity, Measuring, Modeling, Simulating Capacitors, and Inductors. From there, you can create a model while co-simulating together with the PCB fixture. That will provide the best comparison between the measurements and the model. The resulting model can then be used in a simulator and the PCB impact will be correctly included. Or, as an alternative, you can use a two-port probe like the P2102 from Picotest to simplify this impedance measurement. You can perform the fixture removal calibration using a short open load, and that's really simple to use with a probe. You use a short that is approximately the same dimensions as the capacitor, and this will remove the physical length inductance of the capacitor, which the EM simulator will automatically add back in to give you the correct result. If you are using a SPICE simulator, it's a bit more complicated. You could use an ideal short rather than the capacitor size short. This will create a measurement of the capacitor and the physical length inductance. However, it won't include the added inductance due to the precise port placements, i.e. the pad distance on the PCB. It also won't include the vias connecting the capacitors to the power and the ground planes. In other words, using a SPICE simulator prevents you from having the ability to include the PCB parasitics. This is where a tool like PathWave ADS allows you to be more successful. As a final example, here is a typical impedance plot of a 47 microfarad ceramic capacitor showing the vendor data versus the measured data. The vendor data is compared to the measured data and then compared to the data with the mounting inductance de-embedded. Here we are showing that the measured capacitor data with the mounting inductance de-embedded is the right model to use with the EM model in simulation. In summary, by having accurate capacitor data, we can minimize the number of capacitors and a design to save costs and valuable printed circuit board area. The measurement of a component is made up of three parts: the physical internal element, the external distance between the pads, and the PCB footprint, where the PCB footprint and the physical distance between the pads are what make up the PCB mount. If we include the mount in the model also, then we will include it twice. The mount must be removed for PCB simulation because EM simulators will automatically include it. The mounting inductance is measured by shorting the pads on the PCB mount, which allows the reference plane to be clearly defined so that the inductance does not depend on the measurement location of the probe points. As an alternative to calibration, you can also de-embed the mounting inductance. However, that also requires you to measure the shorted PCB mount. The last key takeaway is that we don't always know or don't really know when we get the data from the manufacturer how they measured it. So we recommend you make your own measurements. This concludes our presentation for today. Thank you so much for attending. Here are some links that can be referenced from today's presentation. Feel free to contact us or connect with us on LinkedIn.